Welcome to Everyday Mathematics. Today we are still on the MIT Integration B Qualifying Exams 2010, and we'll be looking at problems 8, 9, 10, and 11. So problem 8 is the definite integral from x equals to 1 to x tending to infinity of 1 over x times the square root of x to the power 4 minus 1. Problem 9 is the indefinite integral of 1 over x times x to the power 5 plus 1. And problem 10 is the integral from x equals to 0 to pi over 4 of the square root of tan x. And problem 11 is the definite integral from x equals to 0 to x equals to 1 of the natural logarithm of 1 plus x all over 1 plus x squared. So these are very interesting problems. Let's go and look at them one at a time. So with problem number 8, which is the definite integral from x equals to 1 to x tending to infinity of 1 over x times x, the square root of x to the power 4 minus 1. So the first thing I'll do is I'll say let y be equal to the square root of x minus 4. So what this means is that y squared is equals to x to the power 4 minus 1. And so if we differentiate both sides, on the left hand side we have 2 dy dx being equal to 4x cubed. And so we can substitute with 2y dy for 4x cubed dx. And then our limits as x and y, as x is 1, that is 1 minus 1, 1 to the power 4 minus 1, y is 0. And as x tends to infinity, y would tend to infinity. So that our integral 1 to infinity of 1 over x times x to the power 4 minus 1 dx. Now to create this guy in the denominator, I'll have to multiply both the numerator and denominator by this. So a quarter comes out beautifully. And in the denominator, we have 4x cubed dx. And then in the denominator, we have to, this one goes to the power 4. And we have x to the power 4 minus 1. So this is the same as a quarter. Now we bring in y, 0, infinity. This is 2y dy over y to the power. Yeah, this is y squared plus 1. And then this is y. So pulling 2 out, this is 2 over 4. And then this becomes a simple so this cancels with that. So we have y squared plus 1 dy. And then when you integrate that, 2 over 4 is a half. We get arctangent of y. It's 0, infinity, 0, infinity. On the upper limit, as y tends to infinity, we have arctangent of that becoming pi over 4, pi over 2, sorry. And at 0, it's 0. So the answer is pi over 4. And this is the answer. Okay, thank you. So let's proceed to the next problem. Problem number 9, which is the indefinite integral of 1 over x times x to the power 5 times plus 1. We'll just say let y be equal to x to the power 5 plus 1. And so when we differentiate both sides, dy dx is the same as 5x to the power 4. And so you can substitute with dy for 5x to the power 4 dx. So our integral now 1 over x times x plus 1. To try and recreate that, we multiply 5x to the power 4, both the numerator and denominator. We get 5x to the power 4 over, so we can pull a fifth out, so that now we just have x to the power 5 here and x to the power 5 there. So this is a fifth, and we have dy over y minus 1 and y. So using partial fraction, we can have now 1 over y minus 1 minus 1 over y dy, which is the same as a fifth natural log of y minus 1 minus a fifth natural log of y plus c. Now y minus 1 from here is the same as x to the power 5, and y here is x to the power 5 plus 1, so this can all be simplified into log of x to the power 5 over x 5 plus 1. This is all in bracket plus the integration constant, and that is the answer there. So this is a very interesting problem, and it's actually very tricky. First thing I would like to do is just use the notation I to be equal to the integral from x equals to 0 to x equals to pi over 4 of the square root of tangent of x dx. Notation J for the integral from x equals to 0 to x equals to pi over 4 of the root cotangent dx, such that when I add I plus j, this is the same as the integral from x equals 0 to x equals to pi over 4 of the square root of tangent of x plus the square root of cotangent of x, which is 4 sine x over cosine x plus cosine x over sine x dx, which is equals to 4 sine x plus cosine x over square root of sine x cosine x, which is obviously equal to root 2 square root of pi square root of 2 from x equals to 0 to x equals pi over 4 of sine x cosine plus cosine x in bracket 2 sine x cosine x. Since I plus j equals to root integral from x equals to 0 to x equals to pi over 4 of sine x to sine x cosine x, which is m as root 2 0 pi over 4 of sine x plus cosine x over root of sine 2x. Right? So this is the same as root 2 0 pi over 4 sine x plus cosine x over the square root of 1 minus sine x minus cosine x squared. So essentially what happens when you square that is sine squared x plus cosine squared x is 1, and then we have negative 2 sine x cosine x, so 1 minus that removes the sine x squared cosine x squared, and so you're left with 2 sine x cosine x, which is the same as sine 2x. So here clearly we see that we could say let u be equal to sine x minus cosine x, such that du dx is equal to sine x, cosine x plus sine x. So du is equal to cosine x plus sine x dx. And this here is the same as this part here. And so we could easily substitute with that. Let's continue. So since we said that our du is equals to cosine x plus sine x, therefore the integral root 2 from 0 to pi over 4 of sine x plus sine x 1 minus sine x minus cosine x squared. This is the same as root 2. Since u is the same sine x cosine x at 0, we have negative 1 since sine of 0 is 0 and upper limit is 0, because sine x and cosine x are the same at pi over 4, and so they subtract out, so we have du over square root of 1 minus u squared. And here we can now just say let u be equals to cosine theta, such that du is equals to negative sine theta d theta. And what happens is now at lower limit we have obviously constant, we have pi, upper limit we have sine of 0 is pi over 2, and then we have du is negative sine theta, and then denominator 1 minus cosine square theta square root is sine theta, so this would cancel out, and so we have root 2 negative theta pi over 2, so this is the same as root 2 times, obviously inverting that, pi over 2. So this is for I plus j. Now we have to look at I minus j, right? So I minus j equals to integral from x equals 0 to pi over 4 square root of tan x minus square root of cotangent x dx, which is 0 pi over 4 sine x over cosine x square root minus cosine x over sine x square root dx. So this is 0 pi over 4, and so we do have square root of sine x cosine x in the denominator, and then we have sine x minus cosine x. Right. As we continue, so I minus j being equal to the integral from, obviously we can put square root of 2 there, pi over 4, and then we have sine x minus cosine x, and then we have 2 sine x cosine x dx. And this is the same as 0 pi over 4, the derivative of sine x plus sine x, right? So that when this is cosine x, the negative, okay, that is correct. So, and then here we have cosine x plus sine x squared minus 1, right? So that we can just say let u be equal to cosine x plus sine x, such that the integral now becomes, at the lower limit, we have, when x equals to 0, cosine of 0 and then sine of 0 is 0, cosine of 0 is definitely 1, and at the upper limit we are looking at the same value there, so we have 2 over root 2. So 1 over root 2 is cosine pi over 4 and also sine pi over 4. And so at the top there we would just say, okay, this is the same as du, because this entire enterprise here is the same as du with this substitution. And then we have x squared minus 1, right? So that becomes a little bit more tractable, and we'll see how we could easily solve that. As we say that I minus j is equals negative square root of 2 from 1 to 2 over root 2 of du square root of u squared minus 1. So this is not really a natural thing. So I could also say let y be equal to square root of u squared minus 1, such that y squared is equals to u squared minus 1, 2y dy du equals to 2u, such that, 2y dy can be used to substitute 2u du. And so getting this down, have negative 2, the limit at 1, y this is 0, at 2 we have 4 over 2, which is 2 minus 1 is 1, so 1 here, and du. So here we have over dy over y, and since this cancels with that, and u is the same as y squared plus 1, so 0, 1 dy over square root of squared plus 1. Okay, and this is, I think, where it becomes a little bit more tractable, and we'll continue in the next slide. I minus j being equal to the negative square root of 2 from 0 to 1 dy y squared plus 1. We could say let y be equal to tangent there, so dy could be substituted of using sec squared theta d theta, and the limits 0 here is 0, 1 there is going to be pi over 4, so we have root 2, 0 pi over 4 sec squared theta d theta, tan squared theta sec theta, this is going to be sec squared theta, so we're going to be left with negative root 2 pi over 4 sec theta, so which is equals to negative root 2, and then we're going to have log of tan theta plus sec theta from 0 pi over 4. So this is negative root 2 log, at pi over 4 we have 1 plus sec theta is 1 over cosine theta, which is going to be 1 over root 2, 1 over 1. So this is just root 2 minus minus, so that's where we're going to be, because at the lower limit tan of 0 is 0, and then sec of 0 is going to be 1, so natural log of 1 is going to be 0. So this is what we are left with for now. So since we have I plus j being equal to root 2 pi over 2, I minus j being equal to negative root 2 natural root 2. When you add this, you get 2i is equals to root 2 pi over 2 negative 2 natural log of 1 plus root 2, divide both sides by I by 2, we get I being equal to root 2 over 4 pi minus root 2 over 2 natural log 1 plus. And so this is going to be our answer for now. So this is a very interesting problem, problem 11, definite integral from x equals to 0 to 1 of natural log 1 plus x over 1 plus x squared. So I think we can begin by saying x be equal to tangent that dx can be substituted with sec theta d theta. Under the limits, when x equals to 0, it becomes 0, x equals to 1, we get pi over 4. We get log 1 plus tan theta over 1 plus tan square theta dx will be sec square theta d theta. And that would cancel with that because 1 plus tan square theta is the same as sec square theta. So you're left with 0 pi over 4 natural log of 1 plus tangent of theta and theta there. So we could play around. Maybe let's use phi. Let phi be equal to pi over 4 minus theta, such that d phi is the same as negative d theta. Okay, so that's a good start. Let's say if I is equals to our integral integrating with, we're substituting with phi being equal to pi over 4 minus theta. So when theta is 0, pi over 4 minus 0, we have pi over 4. Pi over 4 minus pi over 4 is 0. Log 1 plus theta, so the theta becomes negative d phi. Now the negative sign allows us to flip the limits, so comes log 1 plus tangent pi over 4 minus tangent 5 over 1 plus tangent pi over 4 tangent phi d phi. This comes from knowing that tangent a minus b is equal to tangent a minus tangent b all over 1 plus tangent a tangent b. So that's where it comes from. As you can see, this goes to 1, this goes to 1, and so what we are left with is our I being equal to the integral from phi equals to 0 to phi equals to pi over 4 into logarithm 1 plus 1 minus tangent of phi over 1 plus tangent of phi plus phi, so which is equal to 0 to pi over 4 log. So when you make this the common denominator, what becomes out of here is 1 plus tan theta plus 1 minus tan. So we have 2 d phi, and this is the same as 0 pi over 4 using the rules of logarithm. So we have natural logarithm of 2 minus natural logarithm of 1 plus tan phi d phi, so it becomes 0 pi over 4 log 2 d phi minus from 0 to pi over 4 log 1 plus tangent of phi d phi, and this is the same as I, so we can pull y onto the left hand side. So we've seen that now I is equals to the integral from 0 to pi over 4 natural logarithm of 2 d phi minus I, and therefore 2I is equals to 0 pi over 4 natural logarithm of 2 d phi, and so I is equals to natural logarithm of 2, so this is a constant, phi 0, so this is divided by 2 with limit 0 and pi over 4 for our phi, sorry, not theta. So this becomes pi over 4 minus 0 divided by 2, so it becomes pi over 8 natural logarithm of 2. And that becomes our final answer. And that was, I think, provided